Good afternoon, Jay. I'm sorry, there's only Jay Lort in the audience. So good afternoon, everybody, to those people who are watching from the web as well. It's my great pleasure to introduce Milan Vojnovic. Milan is a researcher from Microsoft Research Cambridge, and he is in part of the system networking research group there. So Milan will tell us about planet scale software update.
Nice. Thank you very much. So hi, it's really great to be here. So the talk is on planet scale software updates done together with my colleagues, Christos, Pablo, and Tomas, who is going to join Microsoft Research Cambridge Lab. So I'm part of a system, we are actually all part of systems and networking group in Microsoft Cambridge UK. The work, so I have this thing, is really facilitated by sort of contribution of some people in terms of interactions from the Microsoft MS-Com and software distribution groups, who also provided us with data that I'll come to it soon. Overview, so the outline of the talk is really give you like an overview what Windows updates are, very brief. And then sort of look at some properties that we investigated, including properties of updates and users. It's more like looking at properties of traffic characterization state. And the second part is looking at dissemination strategies. So let's say looking at dissemination strategies including caching and also peer-to-peer with and with no locality in sampling. Yes. In summary, so some sort of highlights of the results include looking at sort of trying to estimate what fraction of the population, user population, is always on. We try to estimate what is the number of machines we believe are always turned on. And so you see, that sort of requires some sort of it's a statistical detection problem. Then also looking at sort of aggregates of queries, trying to understand whether they are sort of smooth in time or there's some inherent estimates and so on. And then looking at patch characteristics in a way you'll see for SP2 and so on. Patches that are sort of many of them, we'll try to see whether we can group them somehow so that they map to users. So users could sort of, a user would sort of download patches only from one of these sort of disjoint groups. So that is also going to be covered. Looking at sort of dissemination problem, so you'll see like we'll try to estimate how many of users are likely behind a cache. We're trying to estimate how many users will be covered by a cache. And then peer-to-peer, so I'll try to sort of cover an analysis that essentially looks at induced traffic flows that cross sort of subnet boundaries. It's like inter-domain traffic induced by peer-to-peer strategy, peer-to-peer delivery. Sort of subnets would be either AS or IP prefix-like subnets. So if you have any question, just please ask at any point.
Are we using Akamai for?
Akamai is used, yes. Akamai and other CD, well, content distribution networks. 35% is essentially looking at entire population, so you'll see, I'll explain, and then trying to figure out, looking at sort of distinct IPs observed, we try to see, I'm going to too many details maybe now, so I believe I'll answer your question this time. So starting with an overview, maybe this is needless to say, like the way, so we have essentially content that is provided, it's software updates. The way it is published is that there is a publisher, whatever, programmers do changes into the code, and then they release sort of certain, okay, let's say there is a need to do a new feature in the code or something, and there is a need to, that sort of induces modifying a set of files, and then basically there is an encoding scheme that produces sort of delta differences with respect to the latest file version, right? And essentially, so we call those deltas, and those deltas get published. So a certain knowledge base, say a feature or whatever, a fix of a vulnerability, results in a bundle of deltas. And sort of a subset of deltas may refer to a file. So this is the content. In terms of the system, nowadays it is essential server system. And it contains like two sort of server types, both update server and distribution servers. So update servers, basically a client comes sort of running an automatic update, say, or driven manually by a human, goes to the update server, checks for updates, gets admitted, say, presume gets admitted, and then if there is a need to download the delta, a patch, it goes to the distribution service. Right. This is like very, very introductory. So in terms of what leads, sort of it gives you a picture of sort of the data, or the nature of the data that we have used in the analysis. So we have both data sets from distribution servers, where actually clients download the content from, and from the update service. The distribution server includes service pack. So we had like from one of the servers, basically IS logs, so service packs, and also packet level network captures from one of the servers. We also got sort of one server data of the Tuesday patch for essentially June, August, and October. This would be like more than a day. This would be like 14 days. But all of these are, in a sense, subsamples looking at, say, roughly guessing like 150 servers, looking just at one of these, or the one in 100. Update servers, I believe this is like a very interesting data set. We got essentially all the queries that go to the update servers over 3 consecutive days, January 04 to January 06, from all the servers. So it's really a large data set and should cover essentially the entire population, which is, say, 300 or approximately 300 million computers. So it's really large scale. So we also use some other things like mapping of the deltas to timestamps and sort of some aside information. So let me maybe try to sort of explain you some of the results. This is just looking at the software update process. So we see basically the patch release times, and this is like a cumulative number of new patches over time. So we see like in between these jumps, sort of almost sort of a steady continuous increase of new patches, and this would be like Tuesday patches that sort of nowadays released every second month in a Tuesday, and we had those jumps, these are like bundle releases of bundle of new updates for, say, SP1, SP2. So first thing was to look at, so we had SP2 data set. We tried to understand what are actually sort of, can we group sort of approximately 200 files, can we group them in a certain way. So the way we did the grouping is essentially trying to, it is used by the following method. So say you have a set of patches, right, and we try to sort of infer what is the pairwise correlation between pairs of patches. So for that purpose, we use like a cosine correlation factor. So what this actually means is that this can be really seen as a geometric mean of 2 probabilities. So one probability being you as a user conditional on that you have, you're looking at the probability conditional on that you downloaded patch I, what is the probability that you download patch A? And the other way around. You take the geometric mean of these two, gives you a coefficient which is symmetric. It's just a metric, right? If this would be equal to 1, essentially means patch I and J are sort of updated always together. Right? So just picking a threshold, 0.9, so we claim, picking up a threshold 0.9, we sort of claim I and J are related, right, are correlated. So that gives you, basically, by doing this, you draw an edge between two patches if the cosine correlation factor is greater than 0.9. It gives you a graph. So if you do that and then you look at the sort of greatest connected component of the graph and you pick up all of those patches that belong to the greatest connected component, you take it out, that's group 1. And then on the residual graph, you again look at the greatest components, group 2 and so on, so you end up having a disjoint groups of patches. As a result, by essentially doing this method, you end up having 26 groups. And note that this is really observing, roughly speaking, 2,000 users and having approximately 2,000 files. We have conditioned on sort of picked up only those users that downloaded more than 1,000 of files. The reason for this one is that the SP2, the trace data set that we had, was really over sort of say order of a day time interval. So we have observed many of sort of partial downloads, people coming and requesting just a few files, which essentially would be sort of resumed downloads from people who sort of started downloading at some point and then continued and so on. So the aim of this thresholding conditioning on downloading more than 1,000 was actually that the aim was to look at those that download the entire package. Right, but this is like undecided part. The thing is that there is like an order. There is like there's 2 orders of magnitude smaller number of groups than the number of the files. And these groups are sort of interpreted in here. So this would be like largest group. This is like a file version ID. File version ID, whenever there is a dark point, corresponds to the correlation factor greater than 0.9. And this sort of has really a natural interpretation in terms of, this largest group would sort of correspond to the core, the core of the operating systems. Smaller groups would correspond to whether Windows Media Player and so on, changes of this kind. So why is this interest? It's lack of generic interest. If you need to disseminate patches, and perhaps you want to bundle patches in a certain way, and you can sort of disseminate them through some distribution channels, say multicast channel and so on, and that this tells you there's no need, to have many channels, but already few. Few order, sort of roughly speaking, in this case, 26 groups essentially are would be sufficient.
What fraction of the user? What's the fraction of that?
Actually, don't know by heart. I may look it up, but I don't remember.
Because that's a common scenario that people are downloading, downloads that you wouldn't want to necessarily put things because the guys who just all they need is just for the piece, and that's the way to
But there is also a notion of a time scale in a way. You have like an observation interval. So imagine you're really picking up, say, 6 hours. That's your observation interval. If you would increase this, then you may see something else. Like there is a bias of that kind. So thresholding is really motivated by that.
Right. Yeah, I see you're trying to, but on the other hand, if some users have such slow connections that they need to download, over the course of days, then just trying to send a multicast channel where you're sending a big patch faster than you I don't know. So the idea behind grouping is that you're going to establish multicast channels and broadcast.
Yes, I understand what you mean. Yes. Yeah, you could also perhaps look at the sub-aggregates. This is also looking at an entire population. You could perhaps disaggregate users into slow, fast, and so on. Yeah, that's it. It is. Yes. Yeah, it's a good one. So if you look at what is the percentage fraction of users covered by these groups. So what this graph shows, ignore the red line. This is looking at deltas, and the blue one corresponds to looking at files, and the previous slide was looking at files. This is just the number of groups, and they are ordered. So group 1 corresponds to the sort of largest group, group 2 second largest, and so on. So what this tells you is that group 1 already covers more than 80% of the users, and then this sort of increases in a sort of a concave way. So it really tells you like that a few groups sort of are sufficient to really cover a large fraction of the users. So moving to user properties. This is one slide on trying to see how updated computers are using a particular method, inference method. The method is to observe that we have this encoding of the patches. So in a way, we deal with deltas. And intuitively, and this was verified, is that the smaller the delta, the smaller the difference should be with respect to the latest file version, right? And that should correspond, if you have a computer, the smaller the delta, the more up-to-date the computer is, right? So this is like an indication of how a computer is updated. And so if you pick up, we picked up a particular knowledge base from TP Juno 5, so it's a particular delta, and so what we plot here is really the patch on it, that is the delta size from smaller to larger, and we have a fraction of users having, this is just a cumulative distribution function, having this given size of the delta. So the graph essentially shows you that there's like a sudden jump for each of those aggregates, country level aggregates. Small deltas already cover large fraction of the user populations, but there is some sort of geographic diversity. So some countries exhibiting a smaller fraction of users having the delta smaller than equal to a value. So the reasons may be various. So perhaps most, very intuitively, a reason would be that in some of those countries we have slower users, more modem users, and they would be patching slower and so on. The computers would be less updated than in other countries.
What was that?
I don't remember precisely now. Let's see. I'm not quite sure, but maybe Internet Explorer or something like that. It was a vulnerability, I believe. Vulnerability fix. There may be different reasons. As I said, you could come up with, and there may be also sort of language-specific reasons and so on, but that would require really a thought. What I would more emphasize is the fact that if you ignore geographical diversities, at least you can observe sort of a jump and so on, which also may not be that surprising given that this is after SP2 release, and people, most of the users do keep do use this automatic updates module turned on sort of by default. So how do sort of queries come over time? The system, so as you will see, is designed in a way that those users do sort of recurrent polling over time, and I'll explain that of precisely what they do, and that should amount to sort of some notion of a smooth query rate over time, say over a day. But we don't see actually, so see what we see. So we started observing, this is for the query up, this is the data from basically to the update servers, queries to the update servers over 3 consecutive days. We started observing from 8 GMT, and what is shown is the number of fresh IPs, distinct IPs, observed in 1 second time. Right? So what you see is that there is certain time of day variability, and then there's a sharp drop on the day 2, and another sharp drop on day 3. Any question?
Yep. That like on one particular second, something will work.
Yeah. So it's essentially it's very intuitive. Basically, you'll see the typical time scale. The polling is mean time between 2 polls, at least for those AOM, for the machines that are constantly on, is like 20 hours. So you expect each computer to poll once in a day, roughly speaking. Okay. So if so, then you would observe from a listing IP a query in the day 1, right, in a normal case. Anything which doesn't occur in day 1 is, in a sense, abnormal. Computer being turned off for a day, and then it gets turned on, query issued, and so on. Right. So it's essentially really the time scale of the...
That's pretty accurately every 24 hours. So that happens exactly 24 hours after the passage of
No, the sharp drop, this is really like 24 hours. I mean, it doesn't have to do anything, it doesn't have to do with the patch release. It's really the way that the polling. So basically those clients, all of those clients, they poll Essential Server. And then they poll with probability 1. Fresh IPs. Downloaded, yeah.
It's fresh. Okay. Fresh in your trace.
In my trace.
Okay.
Yeah, really taking the viewpoint of AGMP. So you're starting to observe from there. You could have taken any other time. You would have a sort of similar picture, but those spikes would be differently positioned. The spikes of the local maxima occur because of the, so say this would correspond 8/9 US time, local time, say, and this would be Asia. Like so, see, I mean, basically those will be contributed by queries originating when you boot up your machine. You come to work, whatever, 9 o'clock, issue a query, and that's why we have those sort of high activity periods, which are sort of synchronized with local times. What this tells you, so we have like, I believe, roughly 180 million distinct IPs observed over a course of 3 days, and 80% of them are observed in day 1, and then there's a significant drop in day 2 and day 3. So it is a good news, and somehow expected, assuming computers are turned on and so on, knowing that the mean time between 2 polls is 20 hours. You should expect that you would see a majority of IPs in a day. Also, you've seen the spikes and so on. If you disaggregate query counts, and now you show just the cumulative number of queries relatively observed up to a certain point, and this is just for day 1, then indeed we have sort of diversity. We have sort of different curves for continent aggregates. So there is this sort of time of day periodicity for the queries. Another example also exhibiting time of day effect. These are 2 ISPs in UK, and this is basically number of requests or queries observed each 10-minute time interval, time bin, over a day. So you see like around whatever, 8, 9, there's a spike. But it is spike like this is larger, the red one is larger than the blue one, and then there is also high activity in the afternoon time, but these 2 basically flip each other. So one is BT, the other one is NTL, 2 ISP, 2 sort of broadband. They do broadband providers. So why do you see why do we have this particular pattern? Could you guess? I mean, why the one has high activity in the morning and sort of a small activity in the afternoon? Yeah, there's like 3M. I don't know quite why. This sort of somehow relates to 3 a.m. a default time that you will have. But the question is why one is having high activity in the morning, and then this is reversed in the afternoon. Would you have any guess why that would be so?
Well, one of the things that's really striking about this graph is that the spikiness, like I mean, the pattern is the same. It goes up and down and exactly the same number of spikes. They're practically, but you would expect it to be random. No way it's the same. And presumably, the only reason the blue one is higher in the ladder is because it's scale that is missing whatever the problem is that.
You could also maybe say that one has more home customers than business customers. I don't know. Yeah, let's say, I mean, this one does have sort of high relative activity in the morning, so it should have more business customers than the blue one, which has sort of high relative activity in the afternoon, which would be home user. Right? So the blue one would have more home user subscribers than the red one, which would be more business customers. But
why is the pattern so practically identical?
I believe, so first you have binning, which is common to all. Also you have this sort of low large numbers effect, so even though it's random, that is averaging because we observe many queries out of these. And they should essentially follow fairly closely. And I believe that the discrepancy is really because of the type of the subscribers they do have. So I won't see that as really surprising. At least in my view. So are they sort of, are the user queries bursty? The question is like, so far what we have seen is really sampling a few ISPs, picking up particular cases and really observing there is a strong time of day effect, and also there may be a discrepancy because of the type of the user or the subscribers and so on. If you want to, so we basically did the test just trying to verify whether for a subset fraction of autonomous system aggregates, we can claim the queries that come from those autonomous system aggregates can be maybe regarded uniform in time. And we have like 18 to 19, I don't remember the number, 18 to 19,000 autonomous systems. So respectively would be almost all. So what we observe, if you sort of make a null hypothesis saying, my null hypothesis saying that a query arrival would be uniform, and I'm comparing that with empirically observed counts of queries, you'll see that the null hypothesis cannot be rejected in, roughly speaking, for half of the ASs, for half of the AS aggregates. You cannot reject the uniformity hypothesis. But the thing is that if you count how many users live in those ASs, you essentially amount to a very tiny fraction, 0.1% of the total number of the users. It is fair to say that this uniformity essentially would sort of in a typical case would correspond to those ASs from which you observe just a few queries. Right. So even though this is like half of the ASs, for a typical AS, which has a decent number of queries coming out, it would exhibit non-burstiness.
The reason you can't reject on a hypothesis is that you don't have enough data.
You could say that, yeah. Yeah, sort of intuitively you would say, a few samples may appear uniform. This is perhaps sort of an interesting bit. So it is of interest to sort of have an idea how many of the computers are always on. And when I say always on, I sort of admit a particular definition of it. So what we know is that users do sort of recurrent polling. So it means like issuing queries. If a computer is always on, issues query by essentially as a sort of time points according to a renewal process random processing time. So what it means in concrete words, assume a query was issued at a time tn. The next query comes is a random time, tn plus 18, this is in hours, tn plus 22, uniformly at random on this interval. So this is the way this polling is defined. Users, that is client machines, can deviate from this, and sort of one typical case is that if you shut down your computer, and you happen to cover the sort of a scheduled query at a point, so you miss the query at this point, you turn it on at some point, and then the query is being issued later on. So you won't be classified, in this case, according to our definition, as being an AOM always-on machine.
What's the paper if you shut down, but let's say it queries and then 3 hours later you shut down, 1 hour after that you turn back on. Is it going to query 20 hours after the previous one, or 20 hours after you start on? Or about 5 minutes after?
So if you shut down in here, it doesn't matter. So then you turn it on, and it would figure out that the scheduled query time is later, and it will be in here. Okay, otherwise, it will be 5 minutes. It will be about the time when you boot it on.
So if the machine is shut down every night, for instance, but it's turned on in the morning, and so you still make queries every 24 hours, it'll look like an always-on machine even though it's off every night.
Mm-hmm. So there's a little twist in the problem. Basically, you have to detect number of AOM machines, but what we observe is really cumulative number of queries. And say a red one would correspond to an AOM query, non-AOM blue one, but we cannot observe those colors. Right? We cannot distinguish one against the other. So the problem is that we can observe cumulative counts, but not AOM counts of the queries. The goal is to estimate the number of AOM machines. But we know something. We know, we know precisely, we have a full statistical descriptions of AOM machines that sort of do independent recurrent polling according to the renewal process, and time between two queries as seen from a query instant has a distribution of this kind, cumulative distribution function. Is just saying uniformly at random on 18 to 22 hours. What is of our interest is not to take that one, but essentially a residual distribution function. Why? Because we start observing from an arbitrary point in time, say 8 a.m. GMT, right? We do not observe a user at his query time thereon, but we are picking up sort of arbitrary point in time, and what we basically just need to map this one to a residual time distribution. So this map is well known. You do it, and essentially what it is if the query is on 0 to 18, it is uniformly at that interval. If it is on 18 to 22, this is essentially just a sort of quadratic band to 1. So this is the distribution that we have, residual time distribution of interquery time. So how do we go with this? The thing to observe is that if I ask you, say, I start observing from 8 a.m., I ask you how many, I assume there is a number of AOM machines, which is M, which is unknown parameter, and I ask you how many queries would fall into the time interval, say, 10 to 11 a.m. What we know is that essentially this random variable is binomial. Just means you have M AOM machines that place their queries, and you just need to count how many of them fall into the time interval 10 to 11. So this is just binomial parameter M and the probability that a query from a specific host land into the time interval. And this is nothing else but A of t minus A of s, and this is the residual time distribution that we have previously seen. So this is one observation. The other one is that there's like a large deviations result that tells you if M is very large, and typically if you take aggregates on a continent, on a large region basis, M will be very large, then this random variable will be highly concentrated around its mean. And its mean is nothing else but M times this thing. Right. So an estimator for M is really taking the counts, dividing them by A of t minus AOS. We cannot observe those counts, but we observe X. We know X, the aggregate number of the counts, counting both AOM and non-AOM, is greater than or equal to X AOM. And essentially, you come up with this estimate, as I said before. What is useful, what is essentially very important to do, is that rely on the fact that we observe sort of these high and low activity periods. So you would like to do this estimator only under sort of over time intervals over which the intensity of non-AOM machines is small. So that would be like overnight night periods when most of the queries would come from AOM machines. Right? It won't be, queries won't come because of the human interactions, humans, sort of booting up their computers and issuing queries. So the estimator is really looking at the minimum over some countable number of those intervals. So this is the estimator. There's like a refined version, but that's out of the scope of the talk. That basically comes with a sort of fixed confidence interval. So if you look at this one, we got this plot. The aggregates here are sort of country aggregates of queries. And what we have is the number of distinct IPs per country. Right? It's like a country size in a sense. It defines size as number of distinct IPs observed from a country. And this is the percentage fraction, the sort of percentage of AOM machines. This is the estimator. So there is a thing which is like, you observe like, for some we have like, very large fraction. But remember, the estimator is an upper bound and also would be a tight bound to the unknown parameter in the cases when the number of AOM machines for those aggregates is large, appealing to the concentration around the mean. So maybe you could sort of ignore whatever is from this point on, and you see that these points sort of fairly sort of settle around a value in a sense. And this is like 20 to 30% the number that, basically 20% that I claimed at the very beginning. Yes?
If this is over the course of 3 days, how many days?
This is basically we have a trace over 3 consecutive days, and we repeated this procedure for each of those 3 days separately, and say then for a country I have like 3 points for each of these 3 days.
If there's a non-AOM machine and it never connects, you won't see it at all. So you're underestimating the non-AOMs because there are some that just they will be off for the duration of that day or 3 days.
Yes.
Also, a non-AOM machine, at the fixed IP, will get a new IP every time it's computed. It needs to be completely expired with a new IP address.
Yes, I agree with that.
So is this over the course of 1 day? So this point was over the course of 1 day?
And essentially it's not even 1 day, but remember the distribution, it really spans. It has a support 0 to 22 hours. And then you run the estimator from, say, 8 plus 22. And then we sort of have repeated for each of those remaining days as well. But it's sort of almost 24 hours time interval.
Yeah, I'm very interested in this. I have a slightly different. I want to know actually what's on that.
Okay, so let me move on to the second part on dissemination strategies and sort of their performance. Current approach is central server, so we have server farm in our own server farm, and also relying on content distribution networks like Akamai and others. Caching is not would be like relying on having caching in some notion of a subnet. In sort of cases, it is not supported because the requests, essentially byte range requests, the way those updates are downloaded, especially not supported by the caches. But say alternative is having to have a cache, sort of a caching infrastructure that would reduce the load on such a server. So nothing fancy so far. Alternative is to disseminate using peer-to-peer. And the obvious appeal of that is the scalability, and sort of being able to sort of absorb flash crowds by the very nature of peer-to-peer systems, bringing the load but also bringing the capacity of the system. So let me just sort of say a few words on the caching and then move on the peer-to-peer performance. So we try to sort of basically in the course of 3 days we observed 180 million distinct IPs, but we also looked at the number of the users because sort of each query, each request, sort of a transaction from a computer to the update server includes certain sort of exchange of files. So you can sort of identify a certain file, track this file, and that file sort of uniquely identifies a transaction which would come from a user. And then counting those, that's like roughly speaking 300 million users. So we see really sort of almost twice as many users as number of distinct IPs. So from a specific IP, we may see more than one request, over a sort of sufficiently over a sort of a short time scale. So what this does is really counting number of repeated requests per IP. So how many requests we see coming out, coming out from an IP. And the distribution of this has like a power law, which is power law. It's like, looks like on the log scale, it looks like that. And so what you can see, what you can do is basically classify on this basis. Classification would mean draw a threshold, and whichever IP has more number of the requests larger than the threshold, you may suspect that that sort of would be a cache or something that covers more than one user. Right. So if you do this thresholding, then you amount to sort of number of users covered by, for threshold 2 is like 62%, and then if you take threshold greater than 50, you sort of have like 20%. So if you take sort of threshold sufficiently large, that should exclude sort of home NATed users. So you can sort of reason on how many users are behind a cache. So this is just inference. So the last bit is on trying to understand, if you run peer-to-peer dissemination, what is the sort of inter-domain traffic, say external download into a subnet. The subnet is, say, AS subnet or prefix, IP prefix subnet, and what is external upload from a subnet. So this is what we would like to understand. How do we characterize, given the subnet size? When I say subnet size, I mean I define subnet size as number of the users living in a subnet. How many of those requests would be, how many of those queries would amount to download from a remote subnet. So I'll come to details of the sort of peer-to-peer dissemination. So if you take like a very simple system, so you have a peer-to-peer system that essentially, so there is a query coming out of a subnet, and that query essentially picks up uniformly at random a peer, an online peer in the system, sort of entirely uniformly at random with no bias to the local subnet. You may ask the question, how many of those downloads would be from remote subnets? If you do this, sort of, very simple global, sort of naive global peering, random peering. So intuitively, it's essentially very simple. Close analysis is that if you have those subnets of bounded sizes, and you have many subnets picking up a user at random, would in most of the cases result picking up a user in a remote subnet. So effectively, essentially, any download would come from a remote subnet, and then any user query would amount essentially to downloading, fetching something from outside a local subnet. So we have sort of simulated this by doing this sort of global random peering and taking the AS subnets. So we mapped we have sort of user population, so we mapped all IPs, each IP to an AS, so IPs are sort of grouped into ASs. And then if you look at the fraction of downloads for a subnet that come from a remote subnet against the subnet size, this is really equal to 1. As I said, I mean, essentially all downloads are sort of from remote subnets. This is not much interesting in a way. It's fairly expected. What is perhaps more interesting is that if you take peer-to-peer, but sort of you're doing something in a slightly more sophisticated way, in a way that you do local subnet preference. So each time you're picking up a user from a local subnet with probability 1, if there exists one. So each time that there is an online user in your local subnet, you fetch an update from him. Otherwise, you go outside, right? So you do this very, very simple locality rule. Now the question is, how this affects this sort of inter-domain uploads and downloads. So this is the question. So if you do it empirically, so again you play this game, but now with locality for essentially our system of AES subnets and users being the subnets. If you look at the number of downloads per AES that come from a remote subnet, so those are those external downloads into a local subnet, and you plot it versus the subnet size, so this is number of distinct IPs in a subnet, you observe something of this kind. So this is with peer-to-peer with locality, and each peer essentially once it pops up, downloads, and then it remains for essentially a minute time interval in the system, so picking up this particular value. Once a 1 minute time interval expires, user essentially becomes offline. So this is the rule. Do you have any feeling why essentially you would sort of observe such a shape? Any intuition for that? Then if you look at the number of sort of fraction of uploads, so say you live in a local subnet and you count fraction of uploads from your local subnet to a remote subnet, how many of those essentially go out compared to the total number, because you count also those that go inside. The fraction essentially observes such a regularity. So you see, if the subnet, local subnet, is sufficiently large, this really sort of concentrates around the value. It tells you that fraction of the uploads to remote subnets from a local subnet is proportional to your subnet size, but this constant of proportionality is a number, unknown number. So this looks interesting actually to sort of figure out what this number is. How does it relate to the system parameters? Another property is essentially an imbalance property. Remember this sort of naive global peering. In that one you can show that you have a balance feature, which is essentially says roughly speaking, the amount of uploads from your local subnet that goes out is balanced to the amount that goes in. So the two quantities are balanced. In here you have, if you look at the ratio of the upload to download, you have such a curve. So there is an asymmetry. So for large subnets, you have more upload than you download. Right? And there is a breakpoint. So basically you can really understand this, and it's fairly easy to describe with a few parameters. So what you need is, first, each host query, you assume that has a density, that's one parameter. So inter-query time of a host is density A, and you also assume that each query stays online for a random time with distribution B. These are two parameters. In here, this is sufficient actually to describe it entirely. Very briefly, the problem is really looking at sort of cover. It's a cover problem. So say so this corresponds to a user query remaining online for some time, then another user query remaining online. This is all happening in a local subnet. And what is your external download is essentially a query that comes and is not covered by any user. So there is no user in the local subnet. So if you basically, this thing is nothing else but counting fraction, that is, how many of these points we have in the total number of these arrows. So it tells you, it tells you essentially this. And if you look at the functional property, this is really parameter n, subnet size. This corresponds to the subnet size. Ignore the integral is really sort of an exponential function with respect to the subnet size. And that essentially is precisely would correspond to this curve. So that's fairly well understood. For the upload, it's very similar, but maybe it's interesting to observe that there is a third parameter, which is the subnet size distribution. And the subnet size distribution essentially sort of is basically defined in this way. So say the distribution subnet size equal, having I users or IPs in the subnet, essentially proportional to the number of the users that live in subnets of size I in the entire system. So we have three parameters. Remember A, B, and this one. And then the number of external uploads, so what comes out of your subnet to remote subnet, is essentially this quantity. R of t is something, whatever it is, depends on the three parameters, but essentially just a sort of a constant, could be regarded as a constant. So you have proportionality with respect to your subnet size. So this is precisely essentially this thing. So there is no magic number. The number that comes out here is really related to three major factors. These are the distribution of the subnet sizes. And then if you do, basically you integrate the equations, you can really fully recover the red lines, fully recover the empirical data. So this is fairly well understood. Why all of this is important, perhaps it's obvious, is that your aim is really to reduce inter-domain traffic, which is sort of a great concern for ISPs, who would not be happy actually that you run a sort of a large-scale peer-to-peer system that amounts to a large upload. So this very naive local subnet preference, it really allows you to reduce crossing the boundary. And by the analysis, essentially, this is essentially the last point to make. By the analysis, you have really a sort of a grasp, a handle on how you need to design your system so that you really sort of reduce the uploads to remote subnets from a local subnet to a sort of a target threshold. So say if you want to reduce this by a factor of 100, and you assume polling as nowadays, like each 20 hours you sort of place a query, you need essentially each peer to remain active for order of a minute. This sort of really gives you sort of a guidelines on how would you sort of configure your clients so as to reduce external sort of inter-domain traffic. So skipping the summary, actually, maybe there's no need to summarize. I may answer any of your questions if you have. Please.
But where the problem, the key problem is that once you do the security, if you do a cache that's trying to fix some problem with security, if you basically do a peer-to-peer, then the first thing that I will do as a bad guy is I will immediately try to protect against or trying to get, once the cache is issued, you can, by entering you can essentially conquer the entire peer-to-peer network which is going to that subject. What are you doing that for? Your entire patent system is collapsed right there.
Certainly, I mean, yes, it's like one of the expected questions. Security issues with peer-to-peer are sort of fairly expected. Apparently, this is like out of the scope of the work. Right, I'm sorry, our aim was not looking... Certainly, I mean, but it's like, designing a peer-to-peer system, and so one issue is the security. That's something that isn't addressed here, essentially. It's really, I mean, our scope was only looking at, very simple peering strategies and how you sort of impact, essentially, network providers. But certainly, yes, I mean, agree that's a question. But that would be like, once you really sort of think of implementing this, I mean, how you do it. And then worrying about those problems. Any other? You? If not, then fine. Thanks. Thank you very much.